Hello and welcome. So in this lecture we are going to study the magnetic fields in matter. Okay, so in the previous classes we have already discussed the electric fields in matter. Now it's time for the magnetic fields in matter. Okay, so we'll begin by taking a magnetic material. Okay, suppose this is our magnetic material. Okay, and we'll not go into the details like whether it's a paramagnetic material or the diamagnetic material or the ferromagnetic material. We'll not go into details right now. We'll only assume that we have a magnetic material. Okay, so this is our magnetic material and we want to find the fields. Okay, we want to find out the fields. So by fields I mean what is the vector potential produced by this magnetic material and the magnetic field produced by this magnetic material. Okay, so this is my goal. Okay, finding vector potential, and from vector potential I can take the curl of vector potential to get my magnetic field. Okay, and one more thing that I want to find is that suppose I am applying external magnetic field. Okay, B external. Okay, what will be the behavior of this magnetic material? Okay, that's also one thing that I want to find out. Okay, how the magnetic properties will change when I am applying the external magnetic field. Okay, so this is my overall goal. Okay, in studying the magnetic fields in matter. Okay, so let's begin. So we'll begin by assuming that the magnetic material is made up of millions and millions of dipole moments, magnetic dipole moments. Okay, so and these magnetic dipole moments will be associated to the electrons dipole moment. Okay, so these will be associated to the electrons dipole moment. Okay, so you can visualize that this we have a magnetic material and we have lots of dipole moment vectors. Okay, or you can also visualize by imagining tiny bar magnets. Okay, and they have the same kind of field. Okay, so bar magnet and the dipole moments have same kind of field, so you can associate bar magnets with that of an magnetic dipole moment. Okay, so classically we know what is the definition of dipole moment. Okay, so suppose we have a current loop. Okay, suppose this is my current loop and through which current I is flowing. Okay, so I have a current loop through which current I is flowing. Then we can define the magnetic dipole moment. It's just I multiplied by integral of dA. Okay, small area elements. Okay, and if we have a planar loop, okay, if we have a planar loop, then the magnetic dipole moment will be simply current times the area of this loop. Okay, but in this case what we want to find is how this magnetic dipole moment is associated to the angular momentum of the electrons. Okay, so remember here we'll be only discussing the dipole moments of electrons. Why not protons or why not neutrons? That I will tell you later on. Okay, why not considering the dipole moments of protons, dipole moments of neutrons? So okay, that I will tell you why. Okay, so right now you just have to remember that we'll be only discussing the dipole moments of electrons. Okay, so before that we want to find the relationship. Okay, relationship between the angular momentum and the dipole momentum. Okay, and that is given by this equation. So mu, that is the magnetic dipole moment, equals to gamma times L, that is the angular moment. Okay, this is the angular moment or angular momentum. Okay, so this is the relation which relates the angular momentum with the dipole moment. Okay, so this is the classical derivation or classical equation. Okay, where this gamma is the gyromagnetic ratio. Okay, gamma is the gyromagnetic ratio, and in classical derivation it comes out to be, so in classical derivations it comes out to be gamma equals to charge upon 2 times m. Okay, q by 2m. Okay, so this is the classical equation, but if we want to extend this equation to quantum realm, what we have to do, we have to simply multiply by extra factor, that is g. Okay, so in quantum mechanics we have this equation, mu equals to g times gamma times L, where this g, this new factor, is the g factor. Okay, and this g factor will change accordingly to the system you are choosing. Okay, so if you are taking electron in an orbit, for that g will be simply 1, and if you are taking electron spin, then g will be g is equals to almost 2. For proton, g equals to 5.5 something. Okay, so it changes depending upon which particle or which system you are taking. And similarly for neutron, g will be equals to minus 3.8, almost equal to minus 3.8. Okay, so in quantum mechanics, this is the relationship between the angular momentum and the magnetic dipole moment. Okay, now I will derive this quickly. Okay, this relationship in classical domain. So this is the relationship that I want to derive. So okay, and for that I will take a very simplified situation, that is I have a charge q of mass m which is rotating in a circular orbit of radius r with a velocity v, and I want to find out this relationship, mu by L equals to q by 2m. Okay, or mu equals to q by 2m L. Okay, where this q by 2m is denoted by gamma. Okay, so it's simple. Okay, so first of all I'm taking this simplified system. For this system, the magnetic dipole moment is simply current times the area of this loop. Okay, I times a, and I can write as charge times the frequency, and frequency here is 1 by t. Okay, and we know the area is simply pi r square. Okay, and time period for this orbital motion I can get from v equals to 2 pi r by t, or t equals to 2 pi r by v. Substituting here, we'll get mu equals to q pi r square v by 2 pi r, and here pi will get cancelled out, r I will get cancelled with this r, so I will get mu equals to q v r by 2. Okay, so this is the angular this is the orbital, you can say simply orbital magnetic moment for an electron which is undergoing orbital circular motion. Okay, and for the same system, if we want to find the angular momentum, that we already know is given by simply L equals to mvr. Okay, and if we take the ratio of mu and L, okay, mu divided by L, if we take, so it's qvr, that is our mu, divided by mvr, that is our angular momentum. It will be equals to qvr by 2 mvr, v will get cancelled out, r will get cancelled out, so it's equals to mu by L equals to q by 2m. Okay, so in classical systems, you'll always find that mu by L equals to q by 2m. Whatever system you take, whether you take a simple charge revolving or orbiting an axis, or you take a charged shell, okay, which is undergoing angular velocity omega, or any solid charged sphere, in all cases you'll find that mu by L equals to q by 2m. Okay, and if you want to extend to a quantum domain, you just have to multiply by the g factor. Okay, so this was the little derivation of this relationship, that is a relationship between mu and L. Okay, so if we have any system which has an angular momentum L, then this equation says that it will also have the dipole moment. Okay, any system having L will also have mu, that is the magnetic dipole moment. Okay, now because we are talking about the electron, so in case of electron there are two kinds of angular momentums present. Okay, so we can have either orbital angular momentum, which is denoted by the L vector, or we can have supine angular momentum. Okay, so for electrons there are two possibilities: either we can have orbital angular momentum or the supine angular momentum. Okay, so by orbital angular momentum I mean that so for orbital angular momentum I mean that the electron is revolving around the nucleus. Okay, and for supine angular momentum you can visualize, okay, that the electron is revolving or it's spinning around its own axis. Okay, but it's not actually true, but you can visualize that electron is spinning around its own axis. Okay, so there are two kinds of angular momentums possible, L and S, supine angular momentum and the orbital angular momentum. So accordingly we will have two magnetic moments, okay, orbital magnetic moment and supine magnetic moment, mu L and mu S. Okay, so we'll use the relationship. So mu L will be equals to minus G, because charge of electron is minus, that's why we have minus here. Okay, G, that is the G factor, times the gyromagnetic ratio times the angular momentum, orbital angular momentum. And if we have the supine angular momentum, then mu S will be equals to minus G E by 2m S. Okay, and then you can use quantum mechanics to find the exact value of these dipole moments. Okay, you can use L equals to under root of L into L plus 1 H cross, where L is the azimuthal quantum number associated to any orbit, and for supine you can use supine quantum number small s. Okay, so these are small s, okay, and this is the capital S. Okay, so supine angular momentum or supine quantum number, and you know that for electron S equals to 1 by 2. Okay, and you can exactly calculate the exact value of mu L and mu S. Okay, so that you can put in the values. Okay, but the main thing is that from this, the supine angular momentum, we have the paramagnetic behavior. Okay, and from the orbital angular momentum we have the diamagnetic behavior. Okay, that we'll see in the coming lectures. Okay, that the reason for paramagnetism is the supine angular momentum. Okay, and the reason of diamagnetic behavior is the orbital angular momentum. Okay, so this is the main important thing that I want you to take away from this lecture, that the paramagnetism is due to the supine angular momentum and the diamagnetism is because of the orbital angular momentum. Okay, now that we'll discuss in the coming lectures. Right now I want to discuss what is the relationship, because we have already discussed the electric fields in matter. We want to find out what is the because we have already studied electric fields in matter. Now it's just a copy paste equations. We just have to copy those equations and apply to in this domain, that is the magnetic fields in matter. Okay, so we have already discussed the electric fields in matter, and we have already discussed many equations that we have already derived there. Okay, so we'll not derive all those equations, we'll just copy those equations. Okay, so before that I want to discuss one thing, that is, because we have to study the magnetic material, so we want to focus on first the basic element of the magnetic material, that is the magnetic dipole moment, single dipole moment. Okay, and I want to find out how it interacts with the external magnetic field. Okay, suppose you have a single dipole moment, and I want to find out how it interacts with the external magnetic field. So first of all, because we have already discussed that if we have a dipole moment P, and if we put in the external electric field E, then there will be a torque, and torque will be equals to P cross E. Okay, similarly here also the torque will be equals to mu cross B, where mu is the dipole moment and B is the external magnetic field. Okay, so the equations are same here also. Okay, and one more thing that we already discussed in electric field matter was the interaction energy. Okay, how this dipole moment interacts with the external magnetic field, and for that we used a simple equation, okay, to calculate the interaction energy. Okay, first of all we assume that our dipole moment, if it is in this position, that is the angle between external magnetic field and mu is 90, then we assume that it is the zero energy configuration. Okay, that is u equals to 0. Okay, and if it is in any other state, like if it is oriented like this, then we can also find the interaction energy. Okay, so this is our assumption, that when theta equals to 90, it is the zero energy state. Okay, and if mu is oriented at any angle theta, then we can also find the energy, and that energy you can use simply this equation, that is the change in internal energy equals to minus times the work done by the external forces. Okay, so you just have to calculate the work done. Okay, and just 1 minute. Oh, anyway, so I will write here del change in energy equals to minus of the work done by external forces. Okay, so if you calculate work, okay, then you can get the change in the energy. Okay, so change in energy, I can write mu at any angle minus u at any angle minus u at when angle is 90 degree. Okay, so u at 90 is 0, so u of theta will be equals to simply minus integral 0 to pi by 2 torque dot d theta. So this is the angular work. Okay, and if you do the integration, and it will come out exactly as that of an equation we have already discussed in electric field matter. Okay, that is mu dot b. In case of if we have a electric dipole moment, then in that case u of theta came out to be minus p dot e. So you will see that the equations are almost similar. Okay, so you just have to replace b with you just have to replace e with b and p with mu. That's all, and all the other equations are same. So this was the single interaction, that is how the single dipole moment interacts with the external magnetic field. Okay, we also discussed, okay, so this was the electrical case. If we have p dipole moment here and electric field like this, then the interaction energy is given by minus p dot e. And we also discussed that if we have a magnetic electric dipole moment oriented in the z direction, and the electric field due to that electric dipole moment will be given by like this. So this was the electric field due to the electric dipole moment, and we have already discussed that this equation is only used in spherical systems. Okay, this is only used in spherical systems. Okay, and if we want to find the coordinate free equation, then this was the equation that we derived. Okay, so this is the coordinate independent form, and this one is only used for spherical system, spherical coordinates. Okay, and we also discussed that if we have now two electric dipole moments, suppose p1 and p2, how will they interact? Okay, and the equation that we derived was like this: u equals to 1 by 4 pi epsilon 1 by r cube p1 dot p2 minus 3 times p1 dot r times p2 dot r. Okay, so from this equation you can see clearly that suppose two electric dipole moments are like this. Suppose this is p1 and this is p2. What will be the interaction energy? U equals to p1 dot p2 will be 0, because dot product of two orthogonally mutually perpendicular vectors will be 0. Similarly here p1 dot r, where r is like this. Okay, it will be 0, it will be 0, so this is the 0 energy configuration. And if we have configuration like this, suppose we have, now suppose this is our configuration p1 and p2. Okay, that is they are aligned in the same direction. Okay, p1 dot p2 will be simply p square if they have same magnitude. So u will be equals to 1 by 4 pi epsilon naught 1 by r cube p square, and p1 dot r will be 0, p2 dot r will be 0 in this case. Okay, because this is again r. Okay, and what about if we have anti-parallel electric dipoles? Again u will be equals to minus 1 by 4 pi epsilon naught 1 by r cube p square. Okay, so these are the three cases that we have discussed in the electrical case. Now in the magnetic case, same equations we have to use. Okay, no change except for that p except that 1 by 4 pi epsilon goes to mu naught by 4 pi. Okay, the only change you have to do is like this: 1 by 4 pi epsilon naught will change into mu naught by 4 pi, or you can simply write, you can simply change 1 by epsilon naught will go to mu naught, and p will be changed to mu, and e will be changed to b, and all the other equations will be same. Okay, so all the other equation will be same. Okay, so this is the torque. Okay, torque produced on the magnetic dipole in the presence of external field, and the interaction energy is minus mu dot b, and the magnetic field produced by the dipole moment, magnetic dipole moment, is mu naught m by 4 pi r cube 2 cos theta r cap plus sin theta theta cap. Okay, remember again, this is only valid for spherical coordinate system. Okay, spherical coordinate system. And if we want to use any coordinate system, then this is the correct equation. Okay, so same as that of an electrical case, except that e's are changed to b, p's are changed to m. Okay, and if we want to find the interaction between two magnetic dipole moments, suppose m1 and m2, then again you have to use the same equation. Okay, and you'll see that if two magnetic moments are like this, it is a zero energy configuration. Okay, if they are parallel to each other, it is the maximum energy configuration, and if they are anti-parallel, this is the least energy configuration. Okay, u is maximum, and in this case u is minimum. Okay, so these are the interactions between a single dipole and the external magnetic field, two dipole moments. Now what we want to find is that, suppose we have n number of dipole moments, or in case say infinitely large number of dipole moments, how will the relation change, and what will be the magnetic field produced by that magnetic material? Okay, so right now we already discussed about the single and two dipole moments. Now we'll deal with the n dipole moments and fields associated with those n dipole moments.